In the preparation, we discussed that ball bearings, deep groove ball bearings, are not just made to support radial loads. They can also support some amount of axial load. And you might want to know, well, how much? So here's an example. If the axial load FA is 263 pounds and the radial load is 2,140 pounds, how many revolutions can this ball bearing here survive with a reliability of 90%? Now we've still got a reliability of 90%, and we know that the dynamic load rating for a radial load is 2,150, and we're looking for the number of revolutions that the bearing can survive, considering that even though the radial load is under the dynamic load capacity, we've got this axial load. Does this put us over the limit? We're going to need this equation here in order to solve that one. This is equation 11-12 in the 10th edition of Shigley, where the applied radial load is F sub r, the applied axial load is F sub a. The equivalent radial load, that means basically what radial load would cause the same amount of damage or cause the same failure as this applied axial and radial load combined. And these factors xi and yi are given in table 11-1. This v here is 1 if the inner ring is rotating, 1.2 if the outer ring is rotating, and 1 for all self-aligning ball bearings. In our case, we have an inner ring rotating, and so we're going to use a v is equal to 1. Now, what is the difference between inner ring rotating and outer ring rotating? Isn't it just a relative rotation? Does it matter which one is fixed with respect to the Earth? So I think this is an empirical phenomenon. I'm not able to come up with any theoretical explanation for why the two would be different. And it doesn't seem to be explained in any of the books that I've found, or in the manufacturer's manuals either. So this is that table 11-1. This tells you as a function of FA, the axial applied load, over C0. This is not C10. This is the static load rating of the bearing, not the dynamic load rating of the bearing. So for our bearing, this is not 2,150 pounds. This is actually 940 pounds is what C0 is here, the static load rating. You look that up, you calculate this number, you find where you are along this plot. You could linearly interpolate or choose maybe the next one on the list. You find out what this value E is, and we're going to use that value of E to compare against, well, we need to calculate something else. The axial load divided by V times FR. This is basically what percentage of the axial load relative to the radial load. If it's very small, if it's less than E, whatever this number E we look up, then our x1 is simply 1 or y1 is equal to 0. This simplifies that the axial load has no contribution, and all of the contribution is coming from the radial load in that case. Now, if our axial load is substantial relative to this number E, then we'll find that we need to be over in these columns here, and we're going to have a different component y2. This axial load is going to have a different effect. And it turns out that for large axial loads relative to C0, we're going to be further down in the table, we're going to end up with them having a smaller contribution, whereas you would find that for small axial loads, as long as you're in this column over here, they're actually going to get multiplied by a larger factor. So we just need to plug and chug. We'll go through the same steps that I listed in the preparation here. So first we look up the static load rating. C0 is equal to 940 pounds for our ball bearing. We're going to calculate the ratio, FA over C0. And that is, we have 263 divided by 940. The ratio is 0.2797. I think we're around 0.28. This is approximately 0.28, right? So we're going to be right here in the table. That gives us, based on that ratio, we're going to find E in the table. So E is equal to 0.38. Then we need to calculate FA over VFR. The table reminds us, if we ever forget what this needs to be. So we've got 263 divided by V in our case. I guess I should say V is equal to 1.0. because we have inner race is rotating. If it told you that the outer race is rotating, you could choose a 1.2. It doesn't say right here, but I think I said in the original problem, assume inner race is rotating, outer is fixed. So v is equal to 1.0. So FR in this case is 2140. So the axial load is a small fraction of the radial load, 0.1229. If FA over VFR is less than E, is that the case? Is 0.1229, is that less than 0.38? Yes, turns out. So these are what we need. X1 is equal to 1.0 for any of them. Y1 is equal to 0 for any of them. That means X1 is equal to 1, Y1 is equal to 0, and I is equal to 1. That is what we're going to use in our equation. So when we find the equivalent load, we say X1 times V times FR plus Y1 times FA. That is equal to 1 times FR plus 0 times FA. That's just equal to FR. So our equivalent radial load in this case is equal to our original radial load, is equal to 2140 pounds force. Because the axial load was so small relative to the radial load, it turns out we don't even have to consider it. It's really not going to affect whether the bearing fails or not. And so we can say, well, our equivalent radial load is 2140. That's less than the dynamic load rating. This thing will survive with 90% reliability for 1 million revolutions. Now suppose we change the problem slightly. The only thing we changed here is that FR changes from 2140 to 526. How many revolutions can the bearing survive now with reliability 90%? So I'm going to go ahead and copy this. All right, what's going to change here? Well, our static load rating is going to be the same. The axial load over the C0 static load rating is going to be the same. It's still 0.28. So E is still 0.38, looking up on the table. Right? FA over C0 is 0.28, so E is 0.38. Now we need to consider FA over VFR. What is that? Well, now we don't have 263 over 2140, we have 263 over 526. That's 0.5. We still have the inner race rotating, so V is 1.0. And now we need to ask ourselves, is FA over VFR less than 0.38? Is 0.5 less than 0.38? No. So we need to move on. This is not going to be true. We're going to need to move on to II. 0.5 is greater than 0.38. That means we need to look up what xi and yi are, and it's going to depend. So we'll bring our table down here. Because FA over VFR is greater than E, we're going to be looking in these columns. It turns out that I is going to be 2 in this case. We're going to have x2 then is equal to 0.56, and y2, corresponding with FA over C0, is equal to 0.28. We have 1.15. Okay, so let's write this out. Our equivalent radial load is equal to x2 then times V times FR plus y2 times FA, where our x2 is 0.56, our V is equal to 1, our FR is equal to 526. We're going to add in 1.15 times our axial load of 263. So our equivalent radial load in this case is 597.01 pounds force. So how many revolutions can it survive? We can use all the same equations as we had above. We can do the same analysis because we have an equivalent radial load. So that's when you've got an axial load. It's just as easy as doing problems with just a radial load, but you have to find what that equivalent radial load is first, and then you can apply all the same formulas. So we know that the force that we apply, or a radial load, times x, the relative life to the 1 over a, is equal to C10, right? And we want to solve for what is our life that we can handle. And so x to the 1 over a is equal to C10 over f. And we can take both sides to the 8th power. And we have a dynamic load rating of 2150. The force that we're actually talking about is the equivalent radial force, 597. And we're going to take that to the a is equal to 3rd power. And we get a relative life of 46.7. So our life is equal to x times our L10 life, 10 million. We've got 46.7 million revolutions under this combined axial and radial load.